Okay. Good evening. Sorry I'm a bit late. Let me think. Where do we start? The first thing is very quickly to bring your attention to the Help Consult and Help Lab that I've called it link, and that does nothing, just gives you the times. I click on that, you'll see the Help Consult, which is me, and the Help Lab, which is Kevin. The purpose, and I say that up there, is you come to see me or Kevin if you're, I'll use the word struggling. You have some problems and you really want to talk to someone. It's not necessarily there for general, you can do your whole assignment just using that 2-hour lab once a week. It's just completely insufficient. There's no new material at that lab, nothing will be handed out, and there's no assessment associated with the lab. It's purely there as a service for you to help you, particularly if you have some problem. Don't expect Kevin to know as much as I do about the assignment. I've done the assignment inside and out for a couple of years now. Not that I can necessarily remember what I did a year or two ago, but he won't have anywhere near the depth of knowledge that I do on the assignment. Okay, so maybe you could use that consultation with me as a better place to go. But from what I've seen on the forum, that's working quite well. I'm trying to come into it more and more as I get more time. So I will try to support Harrison as much as I possibly can when I think that maybe we need something a little bit more than just technical information, more course information. I'll certainly come into it. And with the assignment, there are a couple of things that issues that some of you who really want to push bounds may come up with, and one of those bounds that you want to push is, I've already noticed it, and it's very quick, it happens so quick, is how big can these boards be? How big can the board be? Start with 2x2, 3x3, then 4x4, 5x5, 6x6, 100 by 100, 1,000 by 1,000, million by million. How far can we go? Now, the bottom line is, I don't want to limit it, but I can't exclude the fact that the system will limit the input data. There are buffer sizes, buffers that it reads. And if there's some limit there, that's fine. I'm not worrying about that. You need a certain amount of common sense here. We're never going to have a 10,000 by 10,000 board. That's ridiculous. I can assure you that. Much, much smaller than that will satisfy me. In terms of practicality, anything more than a 5 by 5 board is impossible to do, except for the most trivial of changes. You just can't conceive of the number of possible steps between any two configurations when you get up to 5 by 5. It's massive. And that's 5 by 5. 10 by 10 is absolutely astronomical. It's ridiculous. Now, 100 by 100 is... But again, I'll come back to the fact that I don't have any limit in my program, but I can't exclude the fact that there'll be compiler limits in there somewhere. Now, I haven't seen them yet with the tests that I've carried out. I believe, by the way, on testing, and I know some students like to have auto-testing, and some courses do that. I don't do that quickly, because testing is absolutely part of the design process. So you need, as part of your development, to decide what test cases you consider necessary. And of course that does mean a good, close reading of the assignment and using the imagination of what kind of input could possibly be testable. What kind of input should be in your test cases. Now that's a decision you need to make as part of your development. You could have some kind of scripting to help you automate the process. I've certainly got a couple, but the only way I use them is not so much in comparing the output of a test case. Microphone is very loud. I think I'll turn it down a bit. That's a little better, I think, yeah. You can automate more the process of having a number of boards in test files and running your executable, the puzzle, across, or giving that data to the puzzle executable and generating an output file. That's as far as I go in my testing, and I, by inspection, just check that the boards I know that are good are indeed solved, or are considered to be solvable, and the boards that I know are not solvable are indeed found to be that way. So you can see that in 2 seconds. To go further than that and talk about expected output and actual output and compare them with a script, I think is going too far. If you like, you can, of course, but it's not part of this course to go that far. It's not about testing as such. But you provide your own test cases is part of the development process. Of course, at some point in the assignment, a little bit later on, when we get to the second assignment, I may give you some more direction about what I consider a reasonable test case and what is unreasonable. The reason I have to do that is it's one thing to say whether the puzzle is solvable, it's another thing to actually solve it. And if you give it the wrong data, you could literally be waiting thousands of years for it to finish. Okay, so that's not much point to that. So I have to give you some direction about what is a reasonable test case and what is just ridiculous. It will never finish. And I'm still talking about a 4x4 and 5x5 board, by the way. You will never, I can assure you, be trying your solution in the second assignment on a big board. And by big, I mean anything bigger than 6 or 7. But that solution, is it solvable or not? In some sense, the sky is the limit, because it's such an easy algorithm. Okay. Now, in terms of lectures, I want to fly as quickly as I can tonight. I want to very quickly finish off the revision stuff. That's all accessible to you. I was on not sure, I think I did the arrays very quickly. With the structs, you can spend a couple of lectures easily on structs, all the implications and things you can do with structs. I want to keep it very simple, particularly at this early stage in the course, knowing that about 50% of you are very, very new to C, and it's just no point talking about it in this high-level technical stuff when half the course is just not following. It's still early days. We need to actually get you up to what I call floor level in C. So we can define structs, which are basically sets of data types. They're non-homogeneous, which means that anything you like you can put into a struct. The point of a struct is very simply to keep data that's related together. That's the basic point of it. So here you see, for example, a day, month, and year comprises a struct for date. Those things belong together, and therefore they should be stored together. So we have a type definition here, struct date, that allocates 0 memory. There's no memory involved. It's purely a definition of int, or char, or float. This happens to be called by you or by me date. It is purely an abstract concept. It has nothing to do with allocating memory. The allocation of memory happens when you assign a variable. Or you define a variable, declare a variable with that type. So here I declare birthday to have type struct date. So there's memory created. That memory, in this case, will be those 3 is. Okay, so this is a very simple example of a struct being used to define a useful piece of data. Almost in the same breath as you talk about structs, you talk about type defs. Believe it or not, I rarely use type defs. It's just one of those syntactic sugar things that I always think hide what you actually want or actually doing. Type def doesn't do anything as such, it just is a shorthand notation. So here I've defined, because I have some cultural objection to the word float, what is floaty or ridiculous, I want to call it, because I'm a mathematician, real. So I've defined my float, redefined it and called it real. Okay, that's my choice, and I use a type def to do that. So I can now use real instead of float. I can do that with int and char if I like as well. With my own set of my own set of types. You create an abstract name, and that abstract name, a type, can be used at the start of every declaration. And you can have your whole set of your own creations as types. That's all the type def does. You have not won anything. It's not going to be faster. It could be more readable if you ignore the fact that the end user's got to say, you've used some type there, what is it? Where have you defined that? So they've got to go looking for it. So you really want to be a bit careful that you don't obfuscate your program by using all these weird and wonderful type names that you have defined yourself and have nothing to do, in a sense, with C. So you don't want to go too non-standard, but you want to make it readable. So I'm not so sure having a type called real is such a good idea. Having a type for, here's another type, def, called pair, where I've got two numbers which are going to mean something. It could be an imaginary number of the real and an imaginary part, for example, or it could be coordinates on the XY axis. So here we have two pairs, a pair of integers which are going to comprise a struct, a unit of data in essence, and we've given that a name pair, and we can use that pair anywhere. So I don't have to use the only difference between this and what I just showed you with that birthday is that I now can use that word PAIR as a real type instead of struct pair. Okay, the word struct doesn't have to appear. So if you have some objection to the word struct, use type defs. I like to keep things as they are, and that, like the flower, have all sorts of this verbose language around them, and I like to see structs when they're structs. And when you put new names in there, and I sometimes think, what is that again? I've forgotten. Particularly when you look at code after a couple of years. Not a problem for you. For me, when you look at your program from a couple of years ago and want to use them again, you sometimes think, what was I thinking then? Why did I call that? Where did I define that? Because you could have these things defined in different places, and through includes, you try to bring them all together. It gets messy. But in any case, a lot of people use type defs. Virtually all C programs use a lot of type defs. And here's the type def for a date, a type definition for time, and a speeding ticket. And you see the information that's stored in the struct is the number plate, the speed, which is a floating point number, the date and the time of the incident, and the whole thing is called a speeding ticket, and that is the type. Okay, it's a bunch of data, very neat, and each field in that struct has its own type. And normally, well, here you can see that these are nested. So T and V in the struct have their own type defs, and that's why they can be used as date. If I didn't do type defs, all I have, you replace those names, speeding ticket, date and time, with struct. There you have to use the word struct in there as well. But this is very readable. Now here's a quick little fragment. Don't use a lot of fragments, but I've left it as a fragment in this case, where I define an array of speeding tickets. I use a hash define that the system can take up to 10,000 speeding tickets in an array, and the speeding ticket declaration of the type defs, all that stuff above is there on lines 3 to 5. Now I define my array, which is type speeding ticket, and I'm printing out all the speeding tickets up to the number of tickets that I have, 10,000 of them, with a format, and here we go with this horrible format specifiers. And we'll look at them one by one to make sure they're right. So, tickets, plate. Plate was a char array. Char array, what's all that about? Well, we have a quick look there, and we see that char is a plate, an array of size 7. An array of size 7 is a string, and we need to be able to print out that string. Here, for example, that is a number plate, and we could have A, B, C, 1, 2, 3, D is an example of a number plate, 7 characters in that number plate, and we print them out as a string. There you see a %s as the first format specifier, and here you see the element from that struct, well, from the array, at that particular index that we're looping through. So we increment the index, I, for each one, 0 to whatever number tickets. We print the plate, we print the speed. The speed is 6.3f, floating point, that's why the f. Then we do this gets interesting. We see d.day, d.month, and d.year. So they're nested. So we say, we've got our ticket I, we then want the date, and we want the day of the date. The date is the D, that's how we defined it. If you look to the top, you see date D, that's the name of that field. So we walked through the type defs, the nested type defs, to get to the actual number that we want to print, where it really is. And in this case we have day, month and year. They're all printed with hyphens between them, so you see here %D, %D, %D. So we have 3 dates here, 3 numbers, all %D, just real numbers, integers, and at some time. The time is 2 fields, 2 integer fields, with a colon between them, and there's t.hour, t.minute. You don't want to get more complicated than that. That's bad enough, in a sense, because it becomes unreadable, and you will make lots of mistakes if you try to get more complicated than one level of nesting. Okay, I think that's a very nice example. Well, what am I doing? I'll show you how to use it and how not to use a struct. Well, here's a little example of a full program where I define a struct, name and salary for a worker. I then now declare W to be a worker, and I also have a WP, which is a worker pointer. It's preceded by star, makes it a pointer. It's a type. Now, it's a pointer to a worker. Now, this is where the people that are not used to pointers are in trouble, and a number of you, maybe even half of you, will be bored stiff for the next few minutes, and others will still not understand, even after the next 5 minutes, what I'm talking about, but you'll be seeing a lot more of pointers for the next week. Okay, so it's going to be the pointer era from now on for a while. So here we see a pointer, WP, and an actual worker and a pointer to a worker. Now the pointer to a worker, that is an address. A pointer is an address. But it's got no value. That address has to be given a value. It actually has to be told where that pointer is. Now we have W, which is defined to be our worker, and we now assign the address of W to WP. That means WP points to that worker. Okay, it's crucial that you understand those 2 lines, line 10 and 12. They define 2 variables. One is a normal variable of type worker, and the other one is a variable of type pointer to worker. The worker is defined, declared, I could be careful I don't use the word define at this stage, declared, and the pointer is declared to be a pointer to that W. Okay, so that's what we've got. Now I'll show you what you should and shouldn't do, or how you get at the information. So here we see the WP is the address. Now I've assigned now the salary for that worker to be 125,000. Now star WP dot salary equals 125,000 will generate a compiler error. The next line, star bracket WP dot salary, line 14, also generates a compile error. And I think you'll quite quickly sort of see what's going on there, that what we've got in line 13 is that the precedence of the star and the dot are not what you think they are. What you're actually getting is the WP.salary is being computed first, and then the star. So the dot has a higher priority or precedence than the star. Star of B is wrong. What we want is star WP and then the salary. You've got to think very clearly about what a pointer is here. The pointer is to the worker, and then you've got the salary. So what we want is the worker, we need the pointer first, the star WP, and then we will extract the salary, or initialize the salary to 125,000. Okay, so when we look at the right way of doing it, which is line 16, W.salary equals 125,000, couldn't be simpler. The dot gives us the notation to actually access the field in that struct, W.salary. But that's not using the pointer. If we're going to use the pointer, we have to put parentheses around the star WP. Okay, that means I first want to go to the worker, and WP is a pointer to the worker. Now I want the field, salary, and I want to give it a value. Okay, understand very clearly what the difference is between the two. It's where you put the brackets, basically. And you'll all be very aware of different precedences of operators in different languages. And because C people are C people, from the very beginning, way back in 1970, 69, 70, when Ritchie and Thompson did all the stuff and thought about the language C, they looked at that straight away, this bracket, star, WP, bracket, line 17, and thought, that looks horrible, that's a kludge, we're not going to do that. Let's change that into something which is more aesthetically interesting and cool. And so they changed the notation to a minus sign greater than being a pointer. So that is pure syntactic sugar. That arrow, minus sign greater than, is a piece of syntax that just says put brackets around the star WP. That's all it's saying. Okay, it's a very simple way of denoting that the thing on the left of that arrow is a pointer. It is not the actual variable itself. It's a pointer to a piece of memory. So you have W.salary or WP pointer salary are the two ways you can initialize that struct. The lines 12 to 14, 13 and 14 are wrong, and you can see at the bottom here the error that you get, and it tells you. We compile it by GCC, and GCC will tell you, don't you mean arrow? Because it realizes that these things is a very common mistake that beginning C programmers do. Write down, forgetting that the precedence of the star and the dot mean that it doesn't work as you expect in line 13 and 14. Okay. In general, you can say that if you have something of some type name, and you have a variable, and you have a pointer. I call it S and star SP. A pointer, SP is a pointer, and the star says the type, that it is a pointer, and I give that pointer the address of S. Then you can do S dot element, or bracket the star SP to say first of this, then the field, or you can use the very sexy arrow notation to make it look like a real C program and to make people think that you really know what you're doing. That's what C programmers do. They like these pointers right through their program. C is about using pointers. The more pointers, the better. Is a general rule in C. Okay. All executable programs that basically I've done until now have just used the void in the main statement. Very normal in Unix is to use the command line arguments. We, C people, I cringe a little bit at saying that, because I don't really consider myself a real C person in a sense. Do not prompt the user. Prompting the user for information is not good. It's very Microsofty. It's of a different kind, a different culture, a different kind of people do that. C tends to use command line arguments, and you can have some real doozies of lots of complicated things on the command line, and they determine they control the program. They're the parameters that get passed to the program. So the argc, argv are very important, and if C wouldn't be C without making it look a lot more complicated than it really is, and I'm not going to help this anyway by the next two examples, I don't think, but bear with me. argc refers to the number of arguments, including the calling program. You often want to know what the program that is being executed is called, and that is the first argument. So one argument is absolutely, argc will never be zero. Because if it's never zero, nothing's called it, and how can you exist if you've never been called? This great philosophical question there. So, it's always what? argv0 is the name of the program that was called there, argv1 is the first argument, argv2 will give you the second argument. argv is a two-dimensional character array. So, no matter what you put on your command line, they're just characters. You could have the number 1, 2, 3, 4, 5, 6, 7, 8, 9. They're 9 characters. They are not numbers. And that's going to be your first headache in 50% of the programs you write in this course. Oh my goodness, I need numbers. I put them on the command line, and I've got to convert them. Okay. So I've got to convert my argvs to numbers in that case, or not, depending on what I'm going to do with those arguments on the command line. So here we have my prompt. I'm working on the computer, and I want to type in, I've got some program, generates an executable, a.out, and it's got 2 arguments. Minus PRE, I made that up, means nothing, and 3 also means nothing. These are completely fictitious. Here's my little program to process those input arguments, minus PRE and 3. The problem I have is I want a program that takes an optional numerical argument, 1, 2, 3, or 4. One of those 4 digits. One of those 4 characters, I should say. I could have had A, B, C, D, but I've taken 1, 2, 3, and 4. If the argument is not one of those characters, then it should print a usage message. Now notice that I said optional. That means it may not be there. So when I parse my command line, which is the first thing I do, and will be the first thing you do whenever you need a command line, arguments, when it's more than just the execution, if you're just running a.out, of course, there's no command lines, arguments to process, and therefore you just have void as your as the argument to main. We've now got argc argv, as you can see by line 4. We have to process those arguments, and we do so by first determining, well, how many arguments have we got? That's argc. First port of call, we need to know how many. Now, I said it was optional, the minus PRE and the 3. Therefore, there could be nothing there. Therefore, if argc is 1, that's fine. Okay, so argc1 is fine, or, that's how C does or. If argc is 2, this is line 6 now, and I convert my first, remember this argv0 is the name of the program, which I'm not using at the moment. I'm just wanting argv1, that's the second argument. Starting with 0, it's the second argument. I convert that from a character to an integer. That's what A to I does. It's used a lot. So I convert my argv1 two-dimensional array. argv1 is the second row, and that is going to be the minus PRE. Oh, sorry, what am I saying? The number. Have I got that right? Did I turn something around? Oh, what am I doing? I'm getting the two things confused. Okay, the program we're playing with here is 1, 2, 3, 4. So I can have one character on the command line. That's all. No PRE. That's the previous example. So here I say I convert my argv1 to an integer, and I test to see whether it's greater than or equal to 1 and less than or equal to 4. I could have also, I think about it now, have said if argv1 is equal to 1 or argv1 is equal to 2, or such a straight comparison of a character array element and the optional elements I've got 1, 2, 3 and 4 treated as characters. I could have done that too. Here I've converted them to numbers, and I've converted and I'm comparing them with 1 to 4 that I know are the acceptable input arguments on the command line. Now we can do something with that, and else, if it's not 1, 2, 3 or 4, I print out a usage message, which is what the thing said. If the argument is not one of these characters, 1, 2, 3 or 4, a usage message is printed. Here is the usage message in typical C, typical Unix fashion. Square brackets mean optional, and the vertical bar means alternatives on the command line in shell. Basically, that's the traditional way of indicating arguments. So we have an optional 1, 2, 3 or 4. That's the way you need to execute this program. And notice that I've got argv0 here, which is the name of the executable. So if I run it, I can VCC, the program is called comarg. Why did I call it comarg? Comarg, I can't remember. I create an a.out, I run a.out with no arguments, does nothing. I run it with 1 as an argument, does nothing. 2, 3, 4, 5. When I run it with 5 as an argument, it comes back with the usage, because it doesn't satisfy the requirement of an optional argument, which must be 1, 2, 3, 4, and nothing else. So if I ran the program with .a.out with the letter A or with the string fed, it will all come back with the usage. The usage, of course, is, in this case, the name of the program, argv0, which is ./a.out, that's how I called it. So all it does is it takes argv0, which is what you type in to call your program. If I call that program Tiger, typed in Tiger, that was the name of the executable, it would come up with Tiger. Whatever you give it as a name, the executable is what argv0 is, and that's what it will print. That's what you use it for, argv0. Second example, a little bit more complex, I think. No, it's almost the same. Take an optional argument line switch called reverse. I think you'll probably be doing a few reverses in the course. And you want your program to reverse data or not reverse data. And if you don't give it the minus reverse switch, then your program will just process the data as it is. And if you give it the minus reverse switch on the command line, you want it to reverse the data. Okay, so how do you process that argument? One simple argument this time, could be a reverse or may not be. So, argv1 is fine, or if it's true, then that argument, argv1, has got to be compared with the string minus reverse. So that's a string compare, and the not of it, because string compare comes back with a 0 if they match. Oh, this is where your head starts to fub a little bit. So string compare is happy. If it's happy that the two strings, the two arguments that's got argv1 and minus reverse are the same, it'll come back with 0. Nothing wrong. It's the same. But the trouble is with true false, we want it the opposite because it's got to be 1 and we're happy. Okay, true is 1. So it comes back with 0, so we do the not of that, and we've then got minus reverse. So if there's a second argument, that would be minus reverse. Otherwise, we'll end up putting the usage statement, which is the usual thing, the square brackets with the switches in them, the vertical bars between them, but there's only one switch, minus reverse. Okay, so here's another example of, and I can run it here. A.out, happy, no arguments. A.out minus reverse, no problems, does nothing. Give it rubbish as a string, and it comes back with the usage command. Okay? This is the user interface that you write. There's nothing to do with anything in the sense that I don't even know what I'm talking about. There's no program as such. It's just handling the user input. Very quickly now through makefiles. A makefile is a way to organize your project, your programs. Makefiles are really handy. Every half-respectable C programmer would have lots of experience with makefiles. First thing you must do is create a makefile. That's what you change to change compilers, to change your flags. You have a file, data file called makefile, which you can execute with the instruction in Linux called make, M-A-K-E. So the makefile is just data. It's something you can read, you can look at, you can edit. So you create this makefile. It consists basically of two things only, definitions and rules. The definitions are there if you want to define something, but you don't have to. The rules mean at least one rule, otherwise there's no makefile. The rule is something, is an instruction that the command's got to do. And you could have a makefile, I was thinking about this but I haven't done it yet, I forgot to do it. You could have a makefile, for example, to automate your testing in the assignment. It's a bit unusual. Normally you'd be using a script, which is sort of an executable thing. It's executed, a bit like a Python would be executed, interpreted language. But you could also do it very easily by using a makefile. And you'll very quickly understand why I say that in a few moments. So here's our makefile with the data, which are definitions and rules. And in this case here, you see you've got a definition, which is assignments, basically, of strings to variable names. These are shell-like, not C-like, shell-like variable names. And rules are of the form, there's a target, colon, dependencies, and commands underneath that, which are tab, followed by the command that you want run. This is the template of a makefile. The fact that there's a tab there make some of you very happy because you'll be very format conscious. For a real Unix person, it's a horrible thing to have to format in this way. A tab is a meaningless piece of white space, and why should it be so necessary? But it is necessary. This is how a makefile is defined. It's most un-C-like, ironically. Certainly didn't exist in the days of Ritchie in the 70s. It's actually quite a late development makefiles. When C programs got very complex, somebody, I've forgotten, I did know once who it was, thought of, we need some way of organising this data, and created this whole concept of the makefile and the make command, and it's just taken over the world. So every C program uses it. Okay, so the definition of defined variables is optional. Then you have the target, the thing that you want to make. That's actually the name, that's actually the thing, the object of the exercise, the aim, the goal. And the commands are how you build that target. The dependencies are the, what would you call it, determine whether you need to build it or not. And that has to do with time. So, easy thing is to look at an example, usually becomes very clear. A very simple makefile that you could just type into your system immediately, because you're going to be doing this time and time and time and time again, is these two lines here. Example 1, EX1, I've called it. You just call it EX if you like, forget the 1. And EX1 is the name of the executable that I want to build. And it depends on EX1.c and EX1.h. So there's my dependencies. The target depends on the two source codes, the C file and the H file, the header file. Assuming you have them, of course. And how does the make utility create that target from those two pieces of source code? It runs the command DCC -03, optimize level 3. I hit it with all cylinders. This is an optimization, C flag. I'm going to compile it. Third level optimization. I want it to really go fast. And my output, little o minus little o, is called EX1, which is the name of the target, and that's the whole point. This is the command of how you build EX1. And of course the source program, I'm using EX1.c. So to build EX1, I run that command. That's the essence of what makefile does. Now, you don't see EX1.h anywhere in that command. That's because it's an include, of course, in the EX1.c. It had better be, otherwise you've got a silly dependency in there. Because what does make do, if you type in M-A-K-E, return, it looks for a make file, M-A-K-E-F-I-E-L-E, with a capital M. I think it's rather a capital M. I don't think it'll find it if it's a little m, but I've forgotten. I haven't done it for so many years, a little m. I can't remember if I will find it or not. But in any case, the capital M certainly works. It will then make or look at the make file, or look for a make file. If it doesn't find a make file, it will report an error. No make file, goodbye. If it finds a make file, it will try to create the first rule that it finds. You can have more rules. But the first one, in this case, is only one, EX1. It will try to create make EX1. And what it does, it looks at the dependencies. And if any dependency is newer than the target, it will remake the target. So if EX1.c has been changed, move over to it, or EX1.h has been changed, presumably move over to it, then it will say, oh, EX1, the executable, is older than either or both the source files. I will recreate it for the user. And it does that by doing the next thing, the thing after the tab, which is the DCC, compilation. That is makefile in a nutshell. It's purely there to help you, so that you don't have to type in DCC space minus capital O 3 space minus little o every time, and you make typos, and you've got to type it in again, and you just get lost, in a sense, with all the other stuff that you're doing, and you get all flustered. And really, all that you want to do is, I just edited the source file, and all you need to do is go make. And if you ever come to the screen and say, where was I? I was editing it. Have I edited it? Can't remember what I did last. Just type make anyhow. And if you have edited and you haven't got a new version of the executable, it'll do it for you. Because you can see the last edit was a time, the date later than the last executable. Time is very important in Unix. It really does pay attention to the time of creation of everything. Everything has a timestamp. That's what I mentioned here, timestamp. And if you have more than one executable, you have a whole bunch of executables. Maybe all of the weekly exercises, EX1, EX2, EX3, maybe you want to do it for every one. If you're going to do something slightly different, different flags, whatever, you can have a different rule for every one. A bit unusual, but it could be done. But if you just type in make, it'll be the first one. If you type in make space EX2, then it'll do the rule for EX2 and forget the rule EX1. So you can tell it on the command line what you want to make. You can also do make EX1 if you like. It's up to you. Now I show you now. Okay, they're the two rules. Now you can use definitions as well to make it a little bit more comfortable. And the definitions I have here I have a C compiler that I define to be GCC, and I have C flags that I define to be just the optimization of 3. Okay, now I can use those definitions in the command $cc gives me the string that's defined by CC. $C flags gives me the string defined by C flags. So they're just expanded. So they're sort of macro definitions, if you like, of strings. Make doesn't know what it's doing. It just takes these definitions, does the substitution, and does the command. It's up to you, of course, to make sure the and C flags is what I called it, but I could have called it Fred and Joe. Okay, because instead of CC, I could have called Fred, and instead of C flags, I could have had Joe. And then I could have said $Fred, $Joe, minus O EX1, EX1.C. Not very readable. Then you probably later on think, what the hell was I thinking at that time? Why did I call them Fred and Joe? So normally you'll see millions and millions of makefiles around the world with CC. Everybody uses CC for the C compiler. It's a name, nothing else. And C flags for the flags. In this case, most often we'll be using GCC, but if you want to play with GCC, just change the D to a G, and you can run your make as much as you like. Okay? There was one problem with that. Just occurred to me. If I change my D to a G to use another compiler, assuming that I've just gone through the D process and created the executables, run them, not happy with the output, and want to try GCC. Okay, I edit my makefile, make my C compiler GCC, and I then do make. What will it do? Somebody who knows makefiles maybe would like to. What will it do? I just edited my makefile after having run my program. Anyone? Nothing, indeed. Excellent answer. When nothing is a good answer, it's great. Nothing is exactly right. Because changing the name of a definition in the makefile does not touch the stamp of the timestamp of either ex1.c, ex1.h, or ex2.c, or ex2.h, assuming that ex2.h. It doesn't change any of the timestamps. Assuming that I just had GCC for the ring, I just used GCC to compile ex1 and ex2, and they're coming up with some funny errors. I don't like GCC anymore, I'm going to go to GCC, it must be better. Maybe it'll work with GCC. So you change the D to a D, and you run it, and you go make, and it does nothing, it just comes back with the prompt. You look, the stupid make them again. I want you to make them again. Then you try make EX1, still comes back with a prompt. Doesn't do anything. But make EX2, still nothing. The problem is you haven't changed the timestamp. It still thinks the executable, or in fact if it's true, the executable is still later than the two source programs. So, what you need to do is you have to touch the source programs, either the C file or the H file. Do I say that here? Don't even know whether I say that. So you have to give one of the source programs, don't even say it, a new time, and you can just hit the editor and rewrite it. You've got to change the edit date, the timestamp of the source file, and then when you do make, it'll rerun that command. And this time it'll be GCC instead of DCC, with the touched, if you like to call it that, source file, because we touched it. Now, there is a command in Unix, it's a beautiful command. So, when you do change the make file, if you know what make should be doing, and make refuses to do it, it's because the dependencies are not right, the timestamps are not what you want, so what you do is you literally type in TOUCH space and then the source file you want to touch. If you change the timestamp on it, and when the source file is more than the executable, it'll rerun the command. So touch and make work hand in hand. I don't know how many times I've typed in touch on Unix/Linux in my life. You often do touch because you say, look, mate, I know what you have to do. You think with your timestamps you know what you're going to do, but it'll be wrong. I want you to remake that thing. So you touch a particular source program and then it will remake with new C flags that you put into the make file or with a new new compiler. Sometimes you muck around with the make file and you want it to recompile, so you have to touch particular source programs to get it to do it. Okay, and here's a little bit of slight extension. You can also have a thing called a target called clean, which gets rid of all the rubbish. And rather than let things accumulate in the directory, I've got a clean here which is no dependencies, nothing after the colon, and the command is remove -f EX1, EX2, A.out, no A.out, EX1, EX2, the object files that are created if they're there, and any core dumps if you've been sed faulty. So all the rubbish that's accumulated, that means nothing. You only want the source programs, you even get rid of the executables here. So to run that clean, you simply type make clean, and they all go away. The -f is there to force it, because, well, sorry, no, it doesn't force it, it actually does it, it doesn't complain when it's not there. Normally, if you do remove space Fred, and the file Fred doesn't exist, it says I can't remove it, it's not there. That's really annoying, because if it's not there, you don't have to remove it, is what I would argue. Don't tell me something I don't want to know, it's just making me think and I don't want to think kind of thing. So, what you do is you can run remove with the -f flags and it won't tell you that it's not there. Because you may not have an executable EX2. You may not have any object files and you may not have a core and you do not want them to come back with all sorts of messages which mean nothing to you, which are irrelevant. You just want to remove the stuff if it's there. That's how you do it, -f flag. Don't complain. Now, asserts. It was out of some frustration a year or two ago that I started with asserts. Students submit their work with assert statements in the code. And that puts my annoyance level up pretty high. So I need to actually tell you, don't annoy me by using assert statements in code that you give me. The reason is, actually it's explained very well when you type in the Linux system, man, short for manual, space assert. And it will come back with this thing here. Assert 3, section 3 of the programmer's manual, include assert.h is what you need to do if you're going to do an assert. It's a way of debugging your program, so you have to have a header file, it's called assert.h, and the system has one for you. And it says, the most important line in a sense is the otherwise. Forget the end debug for the moment. The macro assert prints an error message to standard error and terminates the program by calling abort if expression is false, that compares equal to 0. So an assert takes a scalar expression, that's in the synopsis. It checks whether that is false. If it's false, if the expression is false, it will print a message. So you've got to give it, as long as it's true, you don't want it to say anything. No complaints. And if something's not allowed to be false, you put an assert statement around it, just to make sure, if it is false, that you get warned. That's the way the programmers think. But an assert is not the way to do it in code that you submit to me in any case. Of course, an assert will abort your program. Stone dead. That's crashing. You have destroyed your own program, in essence. That may be good in the development sense when you say, look, if that is, some condition has happened, I don't want to go any further, that may be what you want, but it's not necessarily what I want when I'm marking your program and I'm running it, and all of a sudden it doesn't abort. And what do I do then when it doesn't abort? You cannot treat or use an assert as a way of handling errors. No assert should be used to handle errors. I go into that in some detail here, and I'll try to simplify it now to something really simple with an example. Here I've got a program which I, for some obscure reason, called divide debug. I'm debugging a divide program, and it has two arguments, numerical arguments, N and D if you like, two numbers, 1 and 2. Divides the first by the second. 1 divided by 2 is 0.5. So that's fine, but obviously we don't want the denominator being 0. That really screws things up. So my program checks that there are 3 arguments: the name of the program, the numerator, and the denominator. If answer is 3, then I do a scanf, which I won't go into now, of the first argument, argv1, and a scanf of the second argument, argv2. They're scanfs, which are string scanfs. Just notice it, but don't think about it if you don't understand it. Those scanfs actually return values that I need to check, but I don't want to overwhelm you at the moment with more syntax. So scanfs read the 2 arguments and convert them in one hit into integers. See the %v. So this shows you another way of implementing that character to integer conversion. I did it before with an A to I, but now I do it using a scanf, which is a, you could say, sexier way of doing it, a more, what would you call it, C-like way of doing it. It's a more sophisticated way of doing it, almost. So in any case, I've read the 2 numbers in, and they are placed in the variables I, or N and D. We'll have to give the address of the variables. That's what scanf insists on. That's all detailed at the moment. I've read the 2 variables, N and D, and now I do an assert that I do not want that D to be 0. If D is 0, oh my goodness, there's a problem. I want to abort. So I'm handling that error. Okay, so what, and if I don't have 3 arguments, including the name of the program, I do a usage, %s, which is the argv0, and the numerator and the denominator. That's what we'll come up with. So I run the program, GCC, I first compile, generates a.out, I give it 1 and 0 to see what it does, and it comes back with a.out, divide, debug, name the program.c, so it has a source name, line 12, the assertion, D is not equal to 0 has failed. It's telling you what went wrong, that your assert has picked up there's a problem with the denominator. Not obviously, and it worked. But this is a user-induced crash. This is nasty stuff. You have killed your own program mercilessly. There's no gradual, what would you call it, stopping of the program saying, I've picked up an error, user, you need to fix this, and then close files and handle everything properly, and then come back to the operating system with the exit status that you normally do. So, for example, that exit success here in line 19 doesn't happen with the abort. It just drops dead. Okay, as a result of that abort. And there's no exit status. So, research telling us this stuff. So, you crashed your own program. You can't send to a client a program with an assert statement in it. Because if that assert triggers an abort, what do you expect that person to do? He will have not a clue what assert is, or what that line of code means, or anything. He'll just see that it stopped working, it's crashed. It also applies to me. If I'm running your program and it doesn't abort, I have to go and look at your source code to see what condition went wrong and try to work out what's going on, which means I have to understand your program. A better way of doing that, a more graceful way, you could say, is you read the two numbers in D using your string scanf. If D is not equal to 0, then you, in line 13, print 1 multiplied by n divided by D. The reason I do that is for the type conversion. N is an integer, D is an integer, n divided by D will truncate. To avoid that, I do 1.0 times n. That converts the integer into a floating point, divides by D. A floating point divided by an integer is a floating point number. It'll print that out as %f. So, if the D is okay, I do it. If the D is not okay, the denominator cannot be 0, and that's what the program reports. So here are two examples of running it with a 0 denominator. Error, the denominator cannot be 0. The program has terminated gracefully, not aborted. And if it's good data, 1 divided by 2, it comes back with 0.5. Okay, now, the caveat on that is that if you look back to the main statement originally on assert, it says, if the macro ndebug was defined, the macro assert generates no code. So you can turn it on and off from outside, from when you run the compiler with this special name ndebug. And when I show you how you do that, so, do I? I hope so. It is used to turn assert on and off. If defined, ndebug says no debugging, no assert, forget it, don't try the assert. If not defined, the assert will be turned on. So if you do nothing, you have the asserts working and crashing your program, which you may want in your development, but don't send it to anyone. And here I've got a really bad program to print the argument on the command line. Here you see I've got my assert.h here, my standard lib on line 4 for the exit success, and my standard I.O. because of the print. So I've got the 3 header files, it's quite a lot, 3. I've got my argc.argv on line 6. My assert says I have to have 2 arguments, the name of the program and 1 more. Then I do a print of that first argument argv1, and then I return success. So if I don't get 2 arguments, I crash the program. That's what that's saying. If there's not 1 argument after the executable name, this program will do an abort. It's a terrible program. Don't really know, I'm giving it to you actually. So below I compile, execute this program with ndebug defined and with it not defined. Do this by using the -d option. So this VCC minus define ndebug. Outside the program, you can define that string and it will turn off your asserts. Now that is obviously something to do in your makefile. So your C flags would have a -d ndebug when you want to run your code without the asserts in there. And you don't have that -d ndebug when you do want your asserts in there. So you put that into your makefile when you do your compilation. The word of warning I've got is, if you submit a makefile, which you generally do, for the assignment you definitely will, and you do use asserts, I'm not forbidding you that you use asserts, I would prefer not to see them, but if you do have them in your code, I will assume that you've got ndebug defined in your makefile. The reason that you send me the makefile with your code is that I can just go make puzzle. And your makefile will do the compilation for me. I don't want to use my own compiler stuff, just in case I don't compile it exactly the way that you want it compiled. I'll of course look at your makefile to make sure that you've not put some weird, wonderful thing in there. But as long as the makefile looks reasonable, then I'll just use your makefile to compile your program. So you can't complain that I use the wrong switches on it. So if you want to have some kind of optimization in there to make it go faster, or some kind of other weird C compiler flag that I don't even know, that you found through thousands of hours of research, that this is really going to make your program fly, okay, go for it. Put it in your makefile, so when I do a make on it, I build the executable that you want me to. But for goodness sake, make sure you've got ndebug defined if you use asserts. I personally think that you probably won't be using asserts at all, or wouldn't have left them in the code, if you're that level of sophistication. Because asserts tend to be a rather blunt instrument that most reasonable C programs wouldn't use. They're just too draconian, too heavy, too nasty. You take them more subtle in your debug, you write your own debug statements. Because asserts, the point is, an assert does not do error handling. Assert just crashes your program. That's a very important difference. Error handling, gracefully exiting when you find there's a problem in your code is what you're supposed to do. Assert is never graceful. It's always an abort. Okay, I'm going to leave that now. That's all more than enough on what I should have done last week. Can I get out of this? Yes, I think. And very quickly go on to lectures 2. And this is necessary, really necessary stuff. A char is 8 bits. I hope you realise that. An int, as it turns out, is 4 bytes, which is 32 bits. When I mention pointers, how big is a pointer now, actually? The answer to that is, well, it depends on what your computer is, its architecture. Commonly, in my day, computers were, even back at the start, 16-bit computers. That means the address space was 16 bits, which means the pointer is 16 bits. Then we went into the 32-bit era. Then we went into the 64-bit, which is what we've now got. When we talk about a 32-bit machine, or a 64-bit machine, we are talking about the size of the address space. A 32-bit machine has a 4 gigabyte address space max. That used to be really big decades ago. Today it's nothing. It's minimal. So a 32-bit machine cannot address enough space, memory space. That's how the world went to 64 bits. It's massive what you can address with 64 bits. It's humongous. I think 18 digits of memory possible. So we have a memory the size of a room, basically. It's a huge amount of memory you could potentially have. So there's virtually no limit on the amount of memory, in a sense. So 64-bit is a huge advancement. But 64 bits is 8 bytes. 8 bits in a byte. 8 times 8 is 64. Okay, so a 64-bit address space, which is what computers are today, will mean the addresses, the pointers are 8 bytes long. Now, you know that, but you may not know that you know that. Maybe you knew that machines are 64-bit, maybe you see that 64 every now and then in the same sentence as a computer. And you now know, all of you, what that 64 means. It means the size of addressable memory. It doesn't say anything about the int or the char. It just says, where can you look? What can I reach? It doesn't say anything about the data that's there, or the size of the data that's there. Because if I go to some huge address, 64-bit address, it could be a char, a character, 1 byte. It could be 4 bytes. It could be an address, which is 8 bytes. So anything could be there. That is determined by your program, what you've defined and declared. So, consider this program here. I'm printing, I've got 2 variables, I and C. I being int and C being char. That shouldn't be too hard to remember. That's why I call them that. I haven't defined them. I've declared them. I haven't said what they are. I haven't said I is 1 or 0 or C is A or Q or exclamation mark. I've just said there's R and there's C. Now I'm asking the machine, in my program I'm saying, tell me the address of I, tell me the address of C. Okay, so we get the address, the ampersand I and the ampersand C. With a typecast. That's the funny thing in a parenthesis void star. We'll talk about that in a moment. So, I'm printing with ampersand I, the ampersand I, equals %P is the format specifier that has to be filled in, if you like, matched with the argument, which is the ampersand I. So the address of I is printed with format %P, is what that's saying. And the ampersand C, the address of C, I'm actually proving I could have typed ADDRESS space, but I think that means to the ampersand that means address. It's easy to remember. So the address of C equals %P, where the %P is the address of C. Couldn't be simpler. Now I'm calling a function called size of to tell me how big the beast is in bytes. Notice there's no special include there. There's line 1 says standard IO and that's it. So size of is known to the compiler. I give it an argument, I or C, and it tells me how big I or C is. You can give it any variable and it'll tell you how big it is, how many bytes it occupies. So, I'm typing out, printing SIZEOF ampersand I equals %LD. I'm printing an integer as %D, but it's a double int, LD. That's the L means long int. Then I'm putting the comma, then SIZ, the whole thing again, and another %LD. So there are 2 things being printed, apart from the strings itself, size of and size of, the size of the address of I and the size of C. Yeah, I, hang on. Yes, of course. On the first hint, I'm printing the size of the address of I and the size of I. The size of the address of I and the size of I. The size of the address of C and the size of C. There are 2 things. All the C programmers think all the time in 2 ways, 2 things. The variable data, I is value 5, and the address of I. That's a dirty big long number, which is where that I is stored in memory. There are two things you've got to think about all the time, because you often use the addresses, because the address is just a pointer, and C is about handling pointers. So I'm printing out here the size of the address and the data itself. Now, and only now, I'm actually assigning values to the data. Because when I say how big something is, I don't say what's in there, I just say how big it is, how many bytes does it occupy. I don't care about the number itself. When I talk about the address of I don't care what the address is, I just want to know how big it is. Size of is size of, in bytes. Now I'm assigning 58 and X to my two variables, just to show that they are really there, and they can be declared or defined. And I'm actually printing I equals %V, and C equals %C. Okay, so this is the normal part. This is what a normal programmer would normally do. You print out the contents of data, B, I, and C. This previous stuff is a bit weird. Okay, so when I run that, do I actually run that? I'm going to go into that link in a moment. Here's that running. I and C now. First thing I say is here, I and C are initialized, uninitialized. I print out their addresses, I then print out the size of them, and I then print out the definitions. Three things, boom, boom, boom. And here they all are. I and C are uninitialized, the address of I is blob, the address of C is blob, the size of the address of I is 8, the size of I itself is just 4. The address of 8 bytes, we knew that. We did know that because we know that it's a 64-bit machine. 64 bits is 8 times 8 bits. So it's 8 bytes. So we know the size of every address is 8. When you see the ampersand, you don't care what comes after it. It's always 8. An address means 8 bytes. No matter what it points to. A struct, I need to see, makes no difference. An address is 8 bytes, full stop, end of story. There's no caveat here, it's just the way it is. So we print out the two addresses and the two actual data elements. So we see we have a character of 1 byte, an int of 4 bytes, and two side offs which have to be 8 bytes. And there are the two values, 58 and X. And there are the two horrible, the address of I and address of C. Who would care and who wants to know those address values? Well, 99% of the time, and probably 99.999% of the programs wouldn't. But C people tend to be different, and those numbers can be meaningful. And really, if you write the best and most perfect C program, what you tend to do is your program sends around between the functions, passes backwards and forwards, pointers. Pointers are numbers like that. You can't look at a pointer and say, oh, that looks right. It's just a mess. It's this horrible long 64-bit address. You have to go to what the pointer points to find out if the program's working. The pointer is a very fast and efficient way because you're not transporting data. You don't care what's at the pointer end, what it's pointing to. You have to know what it is, of course. And that's why what was all the Blutzer, somebody made the comment of, surely in the assignment we have to define the data structures. This is a data structure course. So yes, of course we define data structures, but no, we don't declare the data structures necessarily in the program. And I've given you in that assignment the task of writing a program with no data structures. But how can there be no data structures? You've got to represent a board. The board is data. It absolutely got structure. Lots and lots of structure. And you start moving those tiles around, my goodness, are you working with structures. And if you think that way, you will write a program that is useless. You can do nothing with. Because it is so inefficient. Typically, to solve the sliding tile puzzle, you will take 4 to 10 billion moves on quite small boards. Not 2 by 2, we're talking about minimally 3 by 3, 4 by 4, and certainly 5 by 5, billions of moves. If you're silly enough to use weightless, my goodness, that won't get past a 3 by 3 simple case. It will bog down after a couple of thousand moves. You cannot use these simple-minded data structures. You must work with pointers. Pointers are simply 8 bytes that move everywhere around and return the logic of the program. You have to change your thinking from the data structure to the data pointer to the structure. Okay, we're thinking in terms of what is pointing to the data and how can we manipulate those pointers to maximize the speed of the program. If you work with real data, it's too slow. It costs you forever to move actual data around the program. You have to do all these moves. Billions of them, trillions of them. So, okay, here's our program. We've actually seen sizes of data and pointers. Now, a program called padding. I notch it up, and instead of I and C, I now have struct S1 and struct S2. Struct S1 and S2 have fields, a character, an integer, and a pointer. And all of you will immediately say, a character, 1 byte. Thinking out aloud. I'm thinking of all of you are thinking out. Characters, 1 byte. Integers, 4 bytes. The pointer, which is the S, is 8 bytes. 8 plus 4 plus 1, 13 bytes. S1 is 13 bytes. S2, character, pointer, integer. 8 plus 4 plus 1, 13. Both structures are 13 bytes long. Great quiz question. Are you even in a state in such a can you even think in those terms? I probably won't ask you. I think the quiz may be your only program, but we'll see. I'd like to ask you about that, which is if you like the theory. Forget the programming. Do you even know what you're doing? Do you know what you're reading? Do you know what you're looking at? Okay, so we have here S1 and S2. The only difference between S1 and S2 is the order of the fields. You see, char is char star. Char star is, of course, a pointer. It's not char, it's char star. S is a char star in both S1 and S2. Okay, so be careful. You don't forget that star. The star is a bit of fluff. It isn't a typo. It isn't an extraneous character. It moves at the pointer to a character. S is a pointer to a character. S stands for someone. S stands for string. Think about it. S stands for string. I'm pointing to a string. The string could be Albert. Deep in memory. And I've got the address of that string, Albert, in my 8 bytes. And that's in S1. Okay, and there's another string there, John. Somewhere deep in memory, and the address of John will be in S2. So I've got 2 structures. They're both pointer strings. How many letters in Albert? 6, I think. I never counted. And John's got 4. So different long strings, but they're just pointers to strings of someone. The string could be that big long thing. Then could be the text of War and Peace. Millions of words. That could be a string. All I've got is the address where it starts. The first letter of lowercase is where it starts. It's a big array, if you like. Okay, now here's my program. And, I forgot to do the most important thing. Yeah, but I'm going to be quick, and if you want to see it for 5 minutes, do it now. Why the void star? In that line there, variable v is our address, %p, which is the format specifier, %p, not b, not %f, %p, p for pointer. And I want the address of v, with this horrible typecast in front of it, void star. Why do I need that? The first thing, the really clever but pedantic students will say is, but sir, the star guide says no casts. Now, if you run that program line, that printf, without that type, it will come back with a warning. I think it's a warning, it's not an error. But it's a nuisance because every time you put %p in there, every time you use a %p without the cast, it'll come back with a warning. If there's on 10 of them, you just throw the screen with a horrible warning saying you don't know what you're doing. The typecast is absolutely necessary. It's not being nice, it's necessary. It could almost be an error, maybe in some compilers it would be. I can't remember whether I tried it with decency and GCC, but I'm sure both will give you a warning at least. So, the C standard says, %p, the argument shall be pointer to void. No discussion. It is a fact. It must be a pointer to void. So when you give it and ask it for the address of some disk, be it a struct, be it an int, be it a char, it will say, I don't like disks. The only thing I give you an address of is something that points to nothing. The address which points to nothing. I don't know why. That was in the compiler. It's standard, it's normal, it's always been that way. For as long as I can remember, in any case of using this, the void star is a necessary type to get the address of a variable. Now, okay, so why so fussy? Well, normally, C is very generous. C will let you imply casts for you. You can get through this course without ever doing a cast at all. Never, not one. In the past, in any case. This course, I don't know whether I'm going to ask you to write the address of something. If I ask you to write, if you see that word address, or the value of the pointer, same thing, and I want to see that number, then you're going to have to use void star. Because you're going to need the address of whatever beast it is. So the void star is the cast you need to use a %p. The reason that you need it is that the printf is what's called a variadic function. 99% of you will never have heard of variadic function, but they sort of make sense when you see that it's a word, because you probably have never occurred to you that when you do a function call that you've created, a function, you know exactly how many arguments there are. So when you call it, you've got to match that. 3 arguments in the function, 3 parameters, and you have 3 arguments in the call. The arguments and parameters have got to match. You know this. You don't anything twice. But think about a printf. Printf is just a library call coming from standard I/O. It's a variadic function. It means you can give it any number of arguments. And it doesn't say one number of arguments if you only give it 1, and it wants 2, you can give it 20, you can give it 100 arguments. And it'll print everything. It's a variadic function. Because it's a variadic function, it's more pedantic. It's more tighter, it's stricter in the casting. It will not cast for you, it wants type correctness. In C, variadic functions, and that's an example of one printf, but there are plenty more, not an awful lot demands, of course, they tend to be very strict in the types, and will complain if you give an argument which is the wrong type. So printf is a case where you cannot assume that it will imply the correct type. Realise one thing, some of you will know what %x is, and that's printing something, a hex number. Instead of an octal number, instead of a decimal number, printed in hex notation, which means it goes up to F, 0 up to F. Don't use that. The reason is never so simple when you see how simple it is. You really think, who knows, a hex number, that address, look at the address that I had before. That was a horrible, long thing with all kinds of G's and F's and A's and zeros in there. That's a hex number. The address is a hex number. But I can't print it as a hex number. What's wrong? It's obvious. But you don't realise it's obvious till you see how obvious it is. This is interesting. So here I have a print of the number 50. 50 in your decimal. You know this. 50. This says a lot to you. But if I print it as a decimal number, %d, I print it as a octal number, or I print it as a hex number. 50. I'll get what you would expect, 50, 62, and 32. 62, 6 times 8 is 48 plus 2 is 50. Oh, it works. The octal representation is 62. The second digit, if you like, is 6 times, is a multiple of 8. So 6 times 8, numbers of 8. So 32 in hex, 3 times 16 plus 2 is 50. So there's the octal representation, hex representation. That's fine, but realise what you're doing. 50 is an integer. You happen to be printing it in octal or hex or decimal, but it is an integer. And we know that int is 4 bytes. We started with this half an hour ago. 4 bytes is an int. Hang on, that %p is printing an address, and that was 8 bytes. So if I give %x as a format specifier, and I'm printing an address, oh dear. The address is 8 bytes, the %x expects 4 bytes, and what it does with the other 4. 8 can't go into 4. It may try to do something, it may warn you, it may give an error, it depends on your compiler. I haven't tried all the things that you can do to upset the compiler. A very forgiving compiler, 64-bit, 8-byte machine, may convert the 8 to 4, but goodness knows whether it's doing something sensible. It may be truncating it, it could be doing anything, it's basically a meaningless exercise. I can't see his torch reflection, is that 20 to 8? I hope it's not 8 o'clock, it's 20 to 8. I really can't see that clock for 17:30. No, that's from... Okay, return to the main page. So that was, by the way, why using %p, and you don't use %x is what I'll eventually go on to. Here, now I'm printing the members of the structures, the size of the structure. Here, line 27, printf, size of A and size of B. I'm now doing a malloc, which is a dynamic memory request. I've got a whole lecture on mallocs coming up. I'm now printing the addresses of the C, I, and S, and I'm doing a malloc for the B structure, and I'm printing the C, S, I. Because they're in different order, CIS, CSI. So, you see at the top here, I'm printing the size of, I've got a macro definition S, because S is defined here to be size of. You can see a little use of #def. I give that just because size of is a long word and it's taken too much room. So I called it S, and I've done a #def SX up here. So these are doing size of the elements, and I'm looking at the addresses So I'm getting, if you like, a dump of the values of the addresses and the sizes of each of the data structures, S1 and S2. Makes more sense when you actually see it. I compile it with the GCC, by the way, for a reason I've forgotten, doesn't matter, and GCC, I do, I remember now, I do both. GCC here, the size of A.C, C is a character, size of A.C is 1, no problem, easy peasy. A.I is an integer, size of A.I is 4, no problem, don't need to think, it's easy. Size of A.S, A.S is a char star is an address of 8 bytes, no thinking required, 1, 4, 8. Now I do structure B. Second line in the output. B.C, B.S, B.I. And I get 184. Nothing's changed, it's the order. I'm doing the order of the declarations. The size of A is 16 and the size of B is 24. What has happened? We've got two serious problems. The first problem is S1 and S2 are the same, it's with a different order of data. But they give different results. One's bigger than the other. The second problem is, why aren't they both 13? Because that's the sum of a character, an int, and an address. 13, 1, 4, 8. Something is going on. I'm even printing the addresses of the CIS and the CSI, which are the fields in the two data structures. So when you see the output, it's a lot easier than the prints. The prints are horrible. It took me a while to get those prints right. And just to make it a little bit more readable, I've given you a somewhat easier to see or understand hex address, faded face. Faded face is a perfectly good hex address, and the real hex address would have been 0A5D, the letters A to F and the digits 0 to 9. That's what hex numbers are. And just because that's horrible, and you keep looking at it, these tracks, I call it all faded face as where it is in memory. So the only thing that's important are the last two digits. Can you see that C is at position 30, I is at 34, S is at 38, B, which comes after A, is at 10, is before 30, and S is at 18, and I is at 20. So B happens before A, even though it was the other way around. So it's going down in memory in the sense of going up. So it's allocating from the top down in memory, apparently. Well, why different? Why larger? Why 16 and 24? And why not both 13? Let's examine the memory requirement. A.C was at 30, but C is 1 byte. And the next element in that struct is I, and that's 4 bytes later, 30, 34. What's 31 and 32 and 33 doing? I don't need them. They're useless. They're wasted. It's ignored. The compiler has put C at 30, and it's put I at 34, and it's thrown 3 bytes away. So it has 3 bytes of padding, 31, 33, and 32 and 33. It then puts AI down, A.I, which take up 4 bytes, 34 to 37. At 38, it then starts the address, AS, the pointer, and that's occupying 48 to 3F. That's the last 3 address, memory element. That's A. Total 13 bytes data actually in memory requires 3 extra bytes of padding for some reason we don't know. So that's where we get 16 from. So A takes 16 as we found at the top here. Remember that? A was 16 here. Now, we're going to find that B, which has a different order, has different padding. So the padding goes, the byte in B is first, as it was with A. It occupies one memory location, which I just called 10, favourite face 10. 11 to 17 are padded. The string pointer here, you see 10, we can look at it here, the output straight off. You become memory readers when you go off C. You look at addresses, and in fact addresses give you a satisfaction that you really are in the machine. You become the computer, you understand what it's doing. There's no abstraction, you're at the level of the computer. You're looking at the actual addresses. So here we're looking at the address for C, which is one character, that's 10. The S, the string pointer to the string Albert somewhere in memory. We don't know where that is, we don't care. Well, we do know where. We don't know how long it is, we can't see that. It's at 18. So 11 to 17 is padding. The address to the string is 8 bytes. So 18, 19, 1A, 1B, 1C, 1D, 1E, and 1F are the 8 bytes for a B.S. B.S, we're doing B. B.S, I'm pointing here, so expecting you to see my finger. So B.S has 8 bytes, and that takes us up to the start of the integer. And the integer requires 4 bytes, 20, 21, 22, 23. And that's everything will be here down here. And variable B, here. 7 bytes to bring us from the char to the string, the address. Then we have 4 more bytes, and to bring us up to the end, now where or why do I see that there are 4 bytes padding from 24 to 27? Let's have a look. 24 to 27. Why do I think, you can't see that, can you? Oh yes, it must be, yes. Those extra bytes here, those 4 bytes, are the extra padding that gives us 24 bytes for the total structure. So we have 24 bytes because there's different padding when you change the order. So the compiler is doing something. It's doing different things for different data when it's just an ordering difference. The difference, the variable A, the char is padded to an int boundary. The char and the int share the same word. Why am I saying that? When we look at A.C, which is 1 byte, it inserted 4 bytes, and then we have the 4 bytes for the integer. So we then have 4 plus 4, which is 8 bytes. 8 bytes is a word in a 64-bit machine. 8 bytes is the address space. Every 8 bytes returns a word. So the char and the int share 1 word in A. In B, that's not possible. The char, after the char, is an address which takes 8 bytes. They can't share the same word, so the compiler has to pad with 7 bytes. Okay, not 3 bytes, because an int and a char can share this room in 1 word. But it can't share with an address, which it takes a whole 8 bytes in itself. So the problem is where we put the address in the data structure. If we put the address at the start or at the end, we're okay. But when we put it in the middle, it increases the size because the compiler pads to get everything to a word boundary. The word boundary comes from a very practical reason. The word boundary is the optimal way of addressing the address space. It addresses in terms of complete 8 bytes. And if you've got new data, it wants to give it its own word as much as possible. It can halve the word and still be reasonably efficient, but the best and most efficient way is to address on 8-byte level bounds. You do not want a program which can address to a character. That is incredibly time-consuming in terms of the address space instruction set of the machine. These are very expensive instructions when it's got to get to a character. It's got to do a calculation. It likes big word addresses in increments of 8, in other words 8 bytes. So that is the optimal way of addressing memory on word boundaries. So the problem, the reason we get padding is to bring things to word boundaries, taking into account that you can share things which are smaller than words. But then you still need some fine padding, smaller padding. But notice as well that between the data there's also padding. So for example, and this will probably test you a little bit, you'll see the CSI, the 20 is an integer. It takes 4 bytes. An integer takes 4 bytes. That brings us up to 24. The A structure starts at 30. So between 24 and 30, we have padding. It does not start a structure in the middle of a word. It brings it up to the next addressable word, which is in this case 30. So from 20, we go to 30. So that's a question, but we ignore the question. But notice one thing, that our program, back to our program, this horrible thing that we haven't really looked at much, is defining char star here and char star here, lines